So that is related to the machine learning in a software-defined optical network. I'm working in a planned group under the supervision of Professor Vittorio Curi. I'm just graduated my PhD last week. So starting my today's presentation from the introduction. So in the introduction, I will briefly describe how important is the cognitive networks for us. Then after that, I will explain about the potential enabler for cognitive optical networks, which is software-defined optical networks and machine learning. After that, this will be the important part of today's presentation, which is application of machine learning in cognitive optical network. That is divided into two parts. The first part is part 1, and the second is part 2. So in part 1, I will explain about the machine learning application for optical networks. That is related to quality of transmission estimation of light paths. And the second part is related to the machine learning for photonic device management, in which I will discuss about the routing evaluation and QT penalty evaluation. So let's begin. So the introduction of 5G technologies, Internet of Things and cloud services marked up a high demand for the traffic capacity enhancement and reliability of optical network. Here you can see from the graph that is taken from the Cisco between 2018 to 2023, the prediction of the global IP traffic that is almost increasing exponentially. To serve this capacity and reliability, different transmission technologies have been proposed in the last decade. That is coherent optical technology, elastic optical networks, and software-defined optical networks. The introduction of these technologies further enhance the capacity and reliability of optical networks, but introduces a high number of tunable parameters such as single carrier, multi-carrier transmission, baud rate, adaptive modulation format, etc. The introduction of these high number of tunable parameters makes the design and operation of optical networks more complex. So generally, we use analytical models for the system modeling, but these analytical models are based on the closed loop formulation, so it needs always some kind of margin to deploy. So the margin that is used for using this analytical model leads to underutilization of resources, which subsequently cause operation expenditure in this case. So what will be the solution? So the solution is the intelligent and cognitive optical networks, which have autonomous and flexible network management, improve and end-to-end communication. They have the ability to automatic learning and real-time decision-making process, and quick recovery in case of network failure. So now I will explain a little bit about the potential enabler for the cognitive optical network. Starting from the software-defined optical network, that's evolved an openness to the networks, and it's separate the data plane from the control plane. Basically, the control plane here is responsible for hardware management, and the data plane is responsible for the data flow management. The next enabler in this direction is machine learning. So what is machine learning? So machine learning is basically a field of study that gives the ability to the computer to learn without being explicitly programmed. So how these two technologies can assist in designing of cognitive optical networks. So here is the architecture of cognitive optical network, which is based on software-defined optical networks. So we have the cognitive unit in the form of machine learning unit agent that has running a different APIs which will perform different network operations. So now let's move toward the cognitive optical networks. So here is the working playground in which we will explore the ability of machine learning. So we suggested a software-defined disaggregated optical network in which we consider the transporter a single optical network element and the optical line system as a single optical network element. The optical line element system consists of the inline amplifiers and fiber spans. So here is the bigger picture of supervised machine learning. This is the second enabler for the cognitive optical network. It is divided in two portions. That is, first is the training portion, which is the time-consuming portion in this phase. So once you have the trained model, so you can implement it, that trained model in the real-time simulation, and you can use it for any kind of applications. So this is the important part of today's presentation. So starting from the application of machine learning towards the cognitive optical network is divided, as I already mentioned, it's divided into two parts. The first one is the machine learning for optical networks, in which I will try to explain about the light part of quality of transmission estimation. The second part is divided into two parts, which is the quality QoT evaluation of the photonic device management and the control and routing of the photonic device management. Now let's extend a little bit in the context of software-defined optical networks. So the light path quality of transmission estimation and QoT evaluation is basically the part of the data plane, while the control and routing is the part of the control plane. So here we are basically tackling both the planes problem with the help of the machine learning. So now I will start the first part, which is basically machine learning for quality of transmission estimation of light path. So before going into details, let's explain how we can characterize the light path QoT. So to characterize the light path QoT, we have to get the abstraction of the network. So the abstraction of the network here is our topological graph, you can see. So in the topological graph, we have the optical line system here as the edges, and the nodes are rodent nodes here. The weights on the optical line system is represented as a QoT matrix, which is here as a GSNR. So GSNR is basically generalized SNR, which consists of the OSNR portion, which is the linear portion, and the SNR non-linear portion. The SNR OSNR linear portion is basically because of the amplified, and the SNR non-linear portion is due to fiber propagation. So here is the first application of the machine learning. So we have the unused network in this. This is the newly developed network. So we have to start a light path deployment. So it initiate a light path request to its controller, which is SDN controller. The controller has a quality of transmission estimator, so it initiates its request to the quality of estimator, which has a deterministic quality of transmission estimator. This quality of transmission estimator gets the nominal parameter from the network vendor and give us a nominal GSNR with some uncertainty. Because of there is a difference of working point, the vendor IDs give you a nominal parameter, so we get a nominal GSNR with some uncertainty. On the top of this, we have an in-service network that is working and is completely developed. So we get the data from this network, and then we put an integrated machine learning API inside the QoT estimator of this network. This is unused network. So we train basically the machine learning model with the in-service network data, and then use it to correct the GSNR uncertainty in the unused network. So here are the details of the two comparisons, which is based on the performance of the machine learning model is assessed by the delta GSNR parameter, which is plotted on the x-axis. So that is representing the GSNR with ML minus the GSNR actual, and GSNR without machine learning minus GSNR actual. So the orange distribution here you can see is the GSNR without use of machine learning. So we have that much error, like in this case we have 1 dB of error without use of machine learning in GSNR estimation, but when we apply a synergic use of machine learning model in parallel with the deterministic algorithm or deterministic quality of transmission estimator, so we reduce almost to the half of the error. So now I will start about today's second topic of my presentation, that is machine learning for photonic device management. So to pursue the application of software-defined optical network down to the layer -1, which is basically the device level, we need to get abstraction of transmission functionality for quality of transmission experiments and for the control, in order to get the full control by the control plane of software-defined optical network. So thanks to the newly developed simulation tool that enable us to get the abstraction of layer -1, that is the device level, and we can get abstraction with the latest simulation tools. With these tools, we can generate data with the abstraction for the particular device, like we are generating for the RODM architecture here, to get a data, and then this data is used to get a machine learning agent trained on this data. So this work is basically done in the collaboration with the Synopsys. Thanks to the Synopsys, they provide us 3 licenses for the photonic device and the simulation. So here is the complete simulation scenario, which have a consists of the transmitter, then we have the receiver, and this is the device under analysis. So the whole simulation is compiled in the OpSim of the Synopsys design suite, and the device under analysis is compiled in the Optical compiler, which is basically the R software. So in this case, we are considering a switch as an architecture. All the other results will be based on this switching architecture. So here is the complete control unit. As you all know about the switching architecture, they are mainly concerned about the routing and then the penalty evolution against that particular routing space. So there are two modules. One is the routing module and the other one is the QoT penalty evolution module. So from the control unit, we get a particular configuration from the user of output configuration of the wavelength that we needed. So we have a machine learning agent that is run on the routing evolution agent, which is trained on a logical model of the device. So this trained machine learning model gives us the states for the particular configuration of wavelengths. These states are then moved towards the penalty evolution module, which has another machine learning agent trained on the transmission simulation data. This machine learning agent provides us a OSNR penalty for that particular output configuration, and then it is transferred to the control unit. So now let's explain a little bit more in detail about the first part, that is the routing evolution. So the proposed technique is validated by three different switching topologies, which is the first one is the honeycomb rearrangeable optical switch, which is the topology is given here. Then we have the Stanke-Bennis and Bennis network. Different configuration of these topologies are represented here. The fundamental building block of these switching topologies is basically a micro ring resonator, which is here, a second order micro ring resonator, which is basically working in a cross-bar state using the control state of 0 and 1. So let's explain about how the data set is generated for this switching architecture. So starting from the case 1, we have the M control states, and then subsequently we have the different lambdas for that. So moving from case 1 to case N, so when we are varying the M control states, we will also get different lambdas at the output. So from case 1 to case 1, moving from case 1 to case 1, we start varying the control states, subsequently we start varying the lambdas, and we get a data set in this configuration. Then this data set is then filled into machine learning module. Here you can see this is basically working as an inverse problem, because we are putting the output, that is lambdas, as a feature, and the M control states, that is the input, as a label. So in the machine learning, we put the lambdas at the output of the, we get at the output of the switching architecture, and then train this machine learning model, and then start testing this for different control states. The accuracy of the machine learning model here is assessed by the loss function, that is the mean square error. So what will be the loss? So the loss is basically the control signal predicted by the machine learning versus the control signal predicted by the actual, which is the actual one. So here is the complete statistics of the data set that is simulated for different configuration of the switching. The data set size for the training of the machine learning basically depends on the optical switching element, that is the main fundamental unit, which is the MMR ring. So increasing the switching, optical switching elements will also increase, you have to increase the training data set for that. So here you can see the heat map that represents the performance of the machine learning. So on the x-axis you have the different rings in the architecture. Here the graph shows for different Bennis or the different switching architecture. Let's consider this one, the Bennis 10 cross test. So the x-axis showing is the rings that is used inside this architecture, and the y-axis showing the intensity of error in predicting the control state. So here you can see, so for ring 24, we have the more error prone. So the machine learning predicted more wrong here. Here is the statistics of the results. So you can see for Bennis 15 cross 15, we have the worst case, which is almost 96% of accuracy with the machine learning for predicting the control state, which is further optimized, and we reach to almost 100% using a simple heuristic in addition with the machine learning module. So now let's explain about the penalty evolution module. So here is the statistics, which is the OSNR penalty against different ports. Here we consider the Bennis 6 cross 6 and Bennis 8 cross 8 for simplicity. These are the 6 ports for Bennis 6 cross 6, and these are the different OSNR penalties that is gain against the data set. So let's consider if we don't know about anything about the statistics of the OSNR penalty, so we have to deploy this worst case OSNR penalty. This is almost 4 dB for BNS 6 cross 6, and similarly almost 3.9 or 3.97 for BNS 8 cross 8. The average margin is less than this. For BNS 6 cross 8, it is like 1.93 dB, and for BNS 8 cross 8, it is like 2.1 dB. This is the average margin. So here are the results for the penalty evaluation. The performance of the machine learning model is evaluated using the delta OSNR. So what is the delta OSNR? Delta OSNR is actually the OSNR penalty actual, and then the OSNR penalty predicted. So here is the delta OSNR. Let's consider the port 1, which is the worst port in BNS 6 cross 6. So here you can see the delta OSNR distribution, which is divided in two sections at delta OSNR is equal to 0. So this portion that is delta OSNR less than 0 is is not that much critical, because in this case we have the OSNR penalty actual less than the OSNR penalty predicted. So we are just losing the capacity, but there will be no effect like on the out of service. But this one, that OSNR, delta OSNR is greater than 0, is the most like prone because if we get here and we miss, so the system will go out of service. So we get the margin here. You can see the maximum margin with the green line. That is almost 0.5 dB for the BNS 6 cross 6. So the margin here is decreases to 0.5 dB on the top of what machine learning predicted. The similar scenario is observed for BNS 8 process with the port 8 here. This is the most worst port in this case. Here you can see that the same scenario happened here. We have the delta that is almost 0.65. So the machine learning decreases from almost 4 dB to almost 0.65 dB, the margin that is needed to deploy for this optical architecture. So the conclusion for today's presentation, so the SDN and the machine learning are the potential enabler for the cognitive or intelligence next generation optical network. The application of machine learning can be utilized on both the control and data plane. The machine learning provides the full abstraction for the network element and possibly a solution for the implementation of SDN concept down to the layer -1. The machine learning approaches can be implemented in a real time because it only needs the time during the initial training phase. So the final remark is the machine learning provides a technological and agnostic solution which can only be relied on data availability. So thank you so much for your attention. If you have any questions, so I will be more than happy to answer.